Okay, hi everyone. How's it going? Decent, medium, Okay, today, let's see, hopefully you guys all figured out Gradescope and turning in the notes. Oh no, sorry, I'm trying to get the camera on the board. We do have at least one student not here. Oh my God. All right, almost, oh no. Okay, so today, we're actually gonna go into the lab pretty soon and actually use Mathematica since I made you watch a video about it. It's a good thing to do. But I didn't quite finish saying the stuff I wanted to say about Riemann sums and some stuff that'll be useful for the lab. So I want to put a few things on the board. And maybe spend hopefully not too long in here. But yeah, talk about Riemann sums a little bit. Maybe say a brief word about how wonderful the fundamental theorem of calculus is, because it lets us bypass Riemann sums, basically. But not every, when you do a definite integral, you anti-differentiate, and not every function has a nice antiderivative. So that's why we still need to do like some Riemann sums and have computers do Riemann sums for us. And we'll see that in the lab today, like some examples. But let me just go ahead. I don't think I even have a real handout or anything. But let me just remind of what we were talking about last time. So, and then we had an example, but maybe I'll pick a different example. So let's say we have f of x is x cubed times sine x on the interval -1 less than or equal to x less than or equal to 3. Okay. And say we want to write down a Riemann sum for this. Actually, I just totally made this function up. So let's see what it actually, maybe I will unmute the screen and see what it looks like. Sorry, we're there. So I'm just going to go to the Google search bar. Google search bar is a great calculator, by the way, and it plots functions too. Times sine x. Put this in parentheses to make sure. Oh wow, it's a weird function. Sorry, let me share screen with the quickly. Okay, so wow, this is a strange function. So, oh, it's very big is the problem. Wait, I need to zoom in vertically. Okay, the Google search bar, like it'll plot functions. Oh my God, what is happening? It's getting confused, I think. Let me zoom out a little bit now. Okay, so it's got something like this where it's pretty horrible, but the x cubed is making it blow up pretty quickly, right? But near, it sort of looks like sine. It's got some sine x aspects of like going back and forth, positive and negative, but the x cubed is making it get big fast. Anyways, I just picked a random function just to show you, like, we can do this for any function, but I'll draw some sort of representation of this. So I put -1 over here and 3 over here. I have to stop sharing the screen, I think. So I'll go back to the board. Okay, so yeah. And I'll try to watch the chat. There's a student watching remotely, so I will try to pay attention to the chat. If you have any questions, please. Okay, so, it looks like something, I mean, I guess it goes through 0, but it doesn't matter. So it looks something like this. And if I want to start building rectangles, right? So there's different ways to do this, but if we did say like a left sum, an individual rectangle would look something like that, right? So these are left sum rectangles. Does that make sense? Top left, we're using the left side of each. So there's these little subintervals, which we could say delta x or delta t or something. And we're using the left side of each interval to pick the height of the rectangle. And if we wanted, say, let's say n equals 1,000 rectangles. Let's make it a sort of a big number. And let's do a left sum, meaning we're going to use the left-hand side of each endpoint, because that's what we were talking about last class, right? About like the fact that you can pick any point in a little delta x subinterval to use to make the height. And left sum just means choose the left-hand endpoint. So the first, or I was calling it like the 0th rectangle. There would be like a 0th rectangle here. Notice this one would peak above the graph because I'm using the left endpoint. So when the graphs go up and down, sometimes you get some differences there. But and I call this the 0th rectangle. It's a 0th rectangle. And this last one would be the 999th rectangle. It's funny, in some ways, right sums are more natural because I would call that if it was a right sum, I'd call it the first rectangle and this the 1,000th rectangle. But the 0th rectangle, well, actually, let's think about this first. What's the delta x here? Like, what's the base of each rectangle? Yeah. So, yeah, how did you get that? Yeah, this is the interval itself is 4 units wide, right? And we're dividing that into 1,000 rectangles. Does that make sense? This is the width. This is the width of the interval. This top right here. Width of the interval. And so that is, I guess, 0.004, which is also 1/250. Good. Okay, so if we did this, the 0th rectangle would be the height, and let me just say f of x. So the height would be f of what? What value would we plug in? Are we agree with that? -1. You plug in -1. So f of -1. What about the first rectangle? Someone tell me. Yeah, negative 0.996, because I would have just moved over 0.004. Yeah, this number is -1 plus 0.004. And then the second rectangle. So there's a pattern here, right? The height is, what's the next one gonna be? Someone else say it. Negative 0.992, and so on, right? And so what we sort of realized is that we can write this, the Riemann sum. And it's funny, I almost don't even care what the specific function is. I can write it down in a second, but it's really like from the 0th to the 999th. Oh, by the way, this also tells you why I'm counting from 0, because this number up here is -1 plus 0 delta x's. And this is -1 plus 1 delta x's. And this is -1 plus 2 delta x's. So I'm counting the number that's right here matches the number that's right there, right? So that's what I'm using to count the rectangles. I'm using how many delta x's I've gone over. Does that make sense? So that's what the count is. Remember, the index is a count. It's a counter. So we're counting something. So that's why this is a counter. Counting rectangles. But it's also counting delta x's. So maybe I'm actually counting delta x's or something. Is the better way to say it. The number of delta x's I'm moving over. And so what you end up with is just f of -1 plus I times delta x times delta x, right? This is the base, the height and the base. This is the thing we were talking about last time. This is the height of each rectangle. This is the base of each rectangle. And so if I wanted to be a little more explicit in terms of something I'd put into a computer, I could write that this is actually the sum from 0 to 999 of, well, delta x we said is 0.004. So this is going to look a little ugly, but it's -1 plus 0.004 I cubed. I did not leave enough room, did I? Damn it. Sorry, let me do this. Let me move this up a little bit and do it. Let me do it over here. So that's going to equal the sum of -1 plus 0.004 I cubed times the sine of -1 plus 0.004 I times 0.004, because that's the delta x. So this whole thing is the height, right? So that might have been a little fast, but let me know if you have questions about what I did there. We also called these like x sub I, these points. And if you plug in I equals 0, you get -1. If you plug in I equals 1, you get that -0.996. If you plug in I equals 2, you get that -0.992 up there, okay? And you could check plugging in 1,000 or 999 that you would get like probably 2.996 just before you get to 3. Yeah, please. Yeah, so if we call these, if we call these points like, if this point was x sub 0, and this point was x sub 1, and this point is like x sub I, this point's x sub I plus 1, and this point here is x sub 1,000, and this point here is x sub 999. You could write it all in terms of these points if you wanted. Those are the points that you're plugging into the function. So that's what So I have to plug it in both places. And then this is delta x. Okay. And the reason I want to write this explicitly is computers eat this up for breakfast. They're excited when you feed this to a computer. We are not excited. Humans are not excited. Computers love this. Now it's not impossible to do that with a finite antiderivative. It's not that fun, but it's not impossible. But I could have come up with something much uglier that would have been even harder. And then that's when you want to feed it to a computer. If you want to actually know an area, estimating an area under a curve, that's when you want to feed it to a computer, okay? So that's with 1,000, and I said the general left sum was I wrote this last time, but I did it kind of quickly at the end of class. So I'm just hoping it will be, it will sort of be a little bit more clear from this example, which is you just do f, actually, so this is f of x, a less than or equal to x less than or equal to b, and n rectangles. So you should check that if you put in like the specific values up there, like -1 and 3 and all that, that you actually get what we get. So you do a plus I delta x times delta x. This was the general formula I wrote down last time at the end of class. That this is basically saying start at A and move over by I copies of delta x to get to the ith point you're going to plug into the function. And if I wanted to be even more explicit, I could write this as a plus I times b minus a over n times b minus a over n, right? Because that's what delta x is. These equal each other by the same argument we gave earlier. It's just the width of the interval divided into n equal pieces. Wow, I'm amazed how many of you are using your iPads to take notes. I didn't notice that till just now. It's awesome. Good investment by Odin. All right. But are there questions about that? We're going to be typing this kind of stuff into the computer. So, or a lot of times I have it for you and you can cut and paste it and alter. But I did want to put that out there. Okay, so then if I want to talk about a couple different sums. So that's the left sum. Maybe I'll just be a little more generic. Let's just say y equals f of x from a to b. So if I wanted what's a right sum instead, right? The difference would be, let me break this into some pieces. So these are all, again, this is sort of our delta x right here. And if I use the right, so I have these, this is 1, 2, 3, 4, 5, 6. I've broken up into 6 pieces, this interval. So if I use the right-hand endpoint, it's like that, right? My rectangles don't look like rectangles, but this is a right sum. Does that make sense? I'm using the top right of each rectangle as on the graph. And so here, if these were the points, again, if this is like x0, x1, x2 through xn, then the first, this would be like the first rectangle, the second rectangle through the nth rectangle, because I'm plugging in this point, I'm plugging in x1. So that's how I'm counting now, right? x1 is the first rectangle. So now the right sum, oh, by the way, I guess on the lab, we're gonna call this like left of n. So I'll just go ahead and write that on the board. So the right-hand sum of n, well, now we're starting at 1 and going to n. So like, because here, like if we were using the right hand of each endpoint, the right-hand endpoint, we would actually get all the way to 3. The last rectangle would have, we'd be plugging 3 into the function, right? And so we get f of xi times delta x is one way to write this. That's the sort of shortest hand way to write this. That's the conceptual way to write this, but again, a computer doesn't know what to do with this. That's why you want to give the computer something much more explicit. But then it's just the same formula because it's the exact same, right? This really was x sub I, the ith point along the x-axis. And so we could write this just as explicitly as the sum I equals 1 to n f of a plus I times b minus a over n times b minus a over n. It's the same idea. It's the same sum, just from 1 to n. Same as the left. But 1 to n instead of 0 to n minus 1. Sorry, I don't know if people over this side of the screen can, this side of the room can see what I wrote. Yeah, please. Right here. Yeah, I wrote it very, this is A plus I times b minus a over n. And the one reason I wanted to write this out is it's kind of fun to, some definition of the word fun, it's kind of fun to see that the last point you're going to plug in really is b, right? And that's actually if you plug in n for I. If you plug in n for I, what happens if I plug in I equals n? That's the last term of the sum is I equals n, right? Well, actually, even up here, where did the specific sum go? This one. If I plug in 1,000, so this stopped at 999, but if I plug in 1,000 for I, if I plug in 1,000 for I right here, what is this number now? It's 4, right? And what's -1 plus 4? 3, which is the right-hand endpoint. So it does work out. You can sort of check yourself to see if you set this up right. See if it works out. And if the same thing here, if you plug in I equals n, the n's cancel, and you get a plus b minus a. What does a plus b minus a equal? B, right? A plus b minus a is b. So you do get b. So just note I equals n. Then this becomes b, which is what you want. That is what you want, right? Okay. Okay, so that is left and right sums. I want to mention briefly, there's these other two types of Riemann sums you can do called trapezoid sums and midpoint sums that might be a little bit better approximations. And we might get to some of that today in the lab if we have time, if I don't talk for too long. Okay, so trapezoid sum. Let me draw this thing again. Here's my, do I have green? Oh, I do. Here's my curve. I'm gonna make it more like up. Okay. And if I take from A to B, you know, I just want to draw you an example of one of these trapezoids. So you still break the number line up the same way into equal pieces. But now instead of a rectangle, what you do is you build a trapezoid. That's called a trapezoid, right? You build a trapezoid to approximate. And maybe here it'll be a little more, it's not perfectly following the graph. Like this looks like it follows perfectly the graph. But do you see how that might be a little better of approximation? Like the rectangles, you get some over or under approximations, right? We get some like overlap or underlap. Is underlap a word? Overlap's a word. So yeah, we get these trapezoids. And so let's see. Let's just say this was like x3 and this was x4. Then, and let me pull this out of the picture and draw it bigger. Well, this is delta x. This height is, so if this is x3 and this is x4, I just picked those randomly, then this height is f of x3, right? And this height is f of x4. And do you know how to find the area of a trapezoid? Like this? Yeah.
So you find the average between f of x3 and f of x4, and then multiply that by.
Yeah, there's this triangle here and this triangle here. So if I think of there being a hinge here, I can sort of flip that. I can flip this little triangle over and make it a rectangle. And this height is exactly halfway between this height and this height. But halfway between is the average of the two, right? So the area is f of x3 plus f of x4 all over 2 times delta x. So that would be the area of a given trapezoid. It turns out that because of this, because you're basically averaging the heights of these two things, the way this is going to work out is that it's the trapezoid sum. If I wanted to like add all the trapezoids up, this is sort of the average of the left and the right. Right? This is the left side. This is the right side. And so I claim that the total trapezoid Riemann sum, if we wrote this out, I'm going to call it trap of n. It turns out that it's the average of the left and the right. Just because we're averaging the left and right side of each rectangle. I can write it all out, but it's like if I added those two sums together and rearranged stuff, I could get something and took a half. I could get something like this expression. Is that at least plausible? You're willing to go with me on that? So that's nice. It turns out that if you want to compute, so the average of the left and right sum actually gives you a better approximation usually. Not always, but usually. Well, actually, probably pretty much always, but that's considered a better approximation. And then, any questions about that trapezoid sum? I mean, that's kind of quick. But then there's also this thing called the midpoint sum. So let me draw this one more time and just try to give you a sense of one rectangle. So if I have from A to B, all right, let's break this up into, let's call A over here. Let's just break this up into a few intervals and call that B. Okay, so what you can do is you can actually take the midpoint of a given. So this is like x1 and x2, right? That's x0. This is the midpoint, which is x1 plus x2 over 2. It's the average of the two is the midpoint. And that's what you're going to plug in to the function to get the height of the rectangle. And so if I drew this for, say, all of these, it's only 4 rectangles, it's not that hard to draw. I would get something like the following. Maybe they should be more like dotted. It's something like that, right? And that's called a midpoint sum. And it turns out that this is actually also a pretty good approximation, like better than left or right. And one reason you might believe that is if I look like right here, notice there's this extra piece there, and then there's this extra piece here. But that's under the graph and that's over the graph. And actually, like, especially when you make small rectangles that are like where the graph's almost straight, when you zoom in on a graph, it usually straightens out, right? You kind of believe that these actually might cancel each other out, like the overlap and the underlap actually cancel. Not perfectly, but they cancel out. They cancel out some. And so you actually get a better approximation. So some cancellation in the overestimate and the underestimates. Estimates make this a good approximation. And so this is called like mid N is what I'm calling this in the lab that you'll see in a second. Okay. Now you can put this into a formula that a computer can evaluate. It's a little bit trickier. What I think I'm gonna do, let me share the screen again. Actually, let me share everything. Okay, so I wanted to show you what the lab is because we'll take a break for a couple minutes and then move into the lab, which is actually upstairs, but oh, is this gonna make me? I think I told it to remember me. No Duo, all right. So if you look at our page and go to the handouts. So today, we actually have this numerical integration lab, and there's a Mathematica notebook, which I'll actually show you also in a second. One thing about this is the way I did this is like you kind of have to go back and forth between the Mathematica notebook and the PDF. And I have some copies of the PDF, but also a lot of you could just bring it up on your iPad if you want to be able to write. That's not, I wanted to open this. Hold on. Sorry, I'll show you guys this in a second. Bless you. Okay, so this is the lab we're gonna do. We're gonna actually look at this integral, the area under the 1 over x curve from 1 to 10. And you might remember that actually has a nice value. But we're going to pretend we don't know the fundamental theorem of calculus, and we're going to have a computer estimate it for us. And we're going to use all 4 of these. We're mainly going to use the left and right, but then the mid and the trap coming in towards the end. I do have some reminders of stuff that you saw in the video. There's also something about, I didn't say in the video, which is how do you enter sums? And it's pretty natural. You can also, hopefully as I imported in the video, as I imparted in the video, you can always click, you can type sum and click on the info button and look at the documentation page. But something like this, right? You just basically tell it what the index is in the range. And then you tell it like what to actually sum. So we're gonna do that. And then there's all these questions. And I also tell you about setting variables and defining functions so that you don't have to type the function over and over again. Of course, 1 over x is not that bad. But if you wanted to change the function to something else and then run all these commands again, it's actually easier to like define it. You can actually define like f of x to always be 1 over x. We'll do that at the beginning of the lab. Okay, hopefully that's nothing, it's gonna be a problem. I did this, I think, on my home computer. I hope the Mathematica version wasn't different enough that it's gonna cause problems. But yeah, so you're gonna go back and forth between the PDF and like the instructions on there. And then the lab itself has, the notebook itself has some of this stuff typed out for you, so you don't have to like type everything super all the time. Although towards the end, after the left and, oops, I left this. I meant to not have that. I ran this command, I guess, and had it there. But then some of the stuff that's later, which we may not get to today, which is fine, is I have you type out yourselves. Does that make sense what we're gonna do? We're gonna go to the lab and just play around with this stuff. What you're gonna wanna do when we get in the lab is log in to Blackboard, find these, and download. Well, get the PDF if you want. I can give out copies of the PDF or get it on your iPad or whatever, and then download the Mathematica lab and open it on the computer and then start working through it. And there's computers enough for everyone, but it's nice if you sit next to people and work together and talk to them and stuff. It used to be there were only half as many computers as chairs in that lab. And it sort of was nice, it forced people to work together. But it's also nice to have your own computer. And if you have a laptop that you have Mathematica installed on, you can use that too. So let's take a break for like 5 minutes, and then we're gonna go up to 216, which is directly upstairs and kind of across the hall. It's like the bathrooms are right there. It's like to the left of the bathrooms, upstairs and across the hall. So let's take a break. Is that cool? Take a break for 5 minutes and then meet up there. And for the Zoom, I guess I'll stop the Zoom, but Olivia, you can hopefully work on the lab yourself and maybe ask questions later or something. Or I can try to log into the Zoom from the lab and you can chat questions or ask me questions there. Okay, so I'm gonna stop the Zoom. I'm gonna Zoom now. Oh, yes, she said sounds good. Okay, all right, guys, let's move it upstairs. Take a few minutes break, stretch a little bit, and we'll meet upstairs and have a good like 40 minutes up there to play around with some of this stuff.